Welcome back to the lab. I hope you've been enjoying this series about Seth, a device that we're building to prevent thermal runaway for our 3D printer. I'm having a lot of fun designing this system, and I'm also enjoying telling you all about it. Now, I'm sure that it's not perfect. I'm sure that our temperature monitor isn't perfect. Maybe we'll find out it doesn't work quite how I hoped it would, but I'm ready to move forward and find out. Let's implement this design physically in Copper. Let's build this system and take it for a test drive. First things first, this design isn't super complex. Because of this lack of complexity, I set out the goal for myself. I want to lay this out using a 2-layer PCB, which I think that will be very possible without needing a lot of time for optimization. I'm hoping that the core content of this video, the layout of the circuit board itself, I don't think that's really going to be interesting enough to talk about for 10 minutes on its own. So let's leverage our time to dive deeper into a few critical concepts. We'll cover isolation, which means creepage, clearance, and comparative tracking index, or CTI. And the next one is a specific struggle that we faced in this design, and that's deciding whether to use an onboard or PCB mount supply that's like off the shelf, or do we want to use an external power brick? Lastly, we need to decide where and how to route cables between the power entry module, the PCB, and the mains exit point. So let's start with the concept of creepage and clearance. For a real product that is being actually tested and certified to meet regulatory standards, there are specific rules that will apply to every product. Funny how that works. Safety standards dictate how much physical separation is required between high voltages, depending on the voltage, and a human in many situations. It also dictates the test voltages that will be applied to ensure that there's sufficient isolation between those two regions, and all of that is specified in these standards and these documents. There are specific rules for both open air from conductor to conductor, that's clearance, and along the surface of an insulating surface, that's creepage. So let's assume that after some careful consideration from a quality engineer and some discussions with the regulatory agency, we all decided to settle on 6730-1 as the safety standard. That one applies to automatic electrical controls and home appliances. That feels kind of right as a gut feel because Seth is automatic, it's electrical, and it controls something. This is just a flat out guess. Anyways, assuming this standard is the one that we picked and it applies to the situation, which I'm not saying it does, which is also a strong assumption, and you should definitely consult an appropriate safety agency. Yeah, you should definitely consult with them for anything regarding safety or a design or an implementation. But anyways, in that standard, there is a table that looks something like this. We can't, I see. Risk? Yes, all right, yeah, ha, just kidding. Let me be very clear. I'm not showing you this table, and I'm not showing you this table on purpose for 2 reasons. Safety standards are living documents, and this video is a snapshot. If I show you a table from 6730-1, it gets updated, this video becomes obsolete. More importantly, we're creating potentially dangerous misinformation. If you search for 6730-1 creepage distance table on Google Images, you may or may not find some search results that I think look something like the table I recognize from 6730-1, but there are also 4 to 5 different tables that come up, probably from previous years or editions of this standard. I recommend that everyone completely disregard those images because they are not a controlled version of 6730-1 and they contain potentially dangerous misinformation. Alright, let me just get off my soapbox for a second. I feel like I've sufficiently CYA'd, as the kids say, so let's talk. Engineer to engineer, let's talk. You want to build something and you want it to control mains, you don't want to kill people, you're not going to certify a $3 PCB from JLC PCB and it's only for you, so you're only going to build one. How do you do it? Well, that's probably a terrible idea. I just want to get that out there. There are some pretty big insurance issues with plugging stuff, especially things that are connected to mains that are not certified or listed with an appropriate safety agency, into the wall. If you burn down your house with something that isn't UL listed, the insurance company may find a way to not cover the damages, the things that were destroyed, the house itself. Be careful. Anyways, electrical safety, HIPOT testing, is a very important part of ensuring electrical safety. This is an objective test that verifies the design provides sufficient electrical isolation from one point to another. It does this by applying a high voltage between them and measuring the rate of change in current. What it's looking for is a detection of dielectric breakdown. You can grab a HIPOT tester off Amazon for less than $300, which is probably the cheapest life insurance you'll ever get. Maybe it isn't the fanciest HiPot tester or the best one, but it's probably better than nothing, so there's a link to one in the description. If you're messing around with mains or you're making your own transformers, buy one of these, use it, test your designs and your implementations before you plug it in with an appropriate voltage, right? You need to test it at the right voltage as described in those safety standards. If your device under test passes, you're good to go. Don't worry about it anymore. Don't forget to throw away whichever board or transformer you actually tested though, because stressing a dielectric with a proper HiPot test can really degrade the dielectric measurably, making it less effective down the road. Dielectrics can wear out, so 3 to 5 kilovolt HiPot test is pretty intense. A HiPot test is one of those things that helps to ensure safety, and a leakage current test is another really important one. Again, the HiPot or high potential test is looking for dielectric breakdown. It's looking to see if an arc jumped across an isolation boundary somewhere. A leakage current test is looking for something different. It's testing how much current can leak across the isolation boundary without overwhelming that isolation when you're applying the rated voltage for the system plus some percentage margin, and then you're measuring the leakage current from one zone to the other. So usually that's through either parasitic or real capacitors that are across that isolation boundary. That could be electrons creeping along the surface of an insulator. That could be through something like an optocoupler. Both of these tests are critical for ensuring safety of a new design, and I would highly recommend that you do both of those things before trusting an isolation barrier. Test your leakage current, test the HiPot. If you aren't familiar with these concepts, you might find yourself a bit confused or overwhelmed. I know I was at first. Hopefully I'm getting some nods in the room, all right? Nod your head if you understand and agree with what... Oh my. Blank stares? Okay, how can we break this down? Let's try to demystify this. Conceptually, what do I do in my schematic or layout to make sure that I'll probably pass a leakage current or HiPot test? What is generally the right approach? Simple. You gotta keep them separated. Yeah, right. You gotta do that. Keep high voltage and low voltage as far apart as possible. It's as easy as that. If your design requires that high voltages need to be closer to low voltages than you'd prefer or that a safety standard would require, then consider adding some routed slots to introduce air gaps between these regions. This generally improves the dielectric withstand of an isolation barrier, so it's generally a good idea. Best to keep these slots wider than a couple millimeters, I'll say 2, so they actually do something. After all, a small enough slot can't withstand any voltage. It's not useful because the electrons will jump across the gap formed by our slot instead of creeping around it. Okay, let's apply these concepts. What did I do to implement an isolation boundary? Well, we started with the worst material group, which is 3B for the standard I'm looking at. Now 3B is a class of comparative tracking index, which is something we were talking about before. That's a measure of how much current can creep along the surface of a particular material compared with other materials. And this is the worst for PCB, like for FR4, 3B. Depending on the material, high CTI coatings can be applied to improve the rating, can move a PCB into a higher class, requiring less distance. Those more advanced materials, those more advanced processes are more expensive. Standard FR4 generally falls into that 3B worst category, which is what we're assuming for now. Pollution degree 2, which is also defined in 6730-1, is a standard environmental set of assumptions. It's like you're assuming that this board is not being rained on, because if this board's being rained on, that's going to drastically change the amount of space required. All right, so basically, we're making a set of environmental assumptions, some material assumptions. We're going to build up a board with 3B materials with an average applied voltage, or a rated applied voltage of 250 volts AC. That requires about... I really don't want you to blindly copy a number in your design. Let's just make up a number, right? Let's call it 5. Let's pretend that there's a safety standard out there exists somewhere that demands 5 units of creepage distance to establish basic insulation for 250 volts AC. Now we need to double that to establish reinforced or double insulation, so we might need something around 10 units. Assuming this is all real and not just a number I pulled out of nowhere, which it isn't, the minimum distance that we should now allow between mains and me is 10 units. So what do you think we'll find in our PCB? 5 units, of course. Wait, that's not right. 11 units. Well, in fact, I did 11 millimeters. Why? No reason. Why am I wasting all that space? Because more is better. And if 10 units were a real requirement and that unit happened to be millimeters, then 11 units would be better. But that is not advice. I just made up a number. This is not in any standard. I made up a unitless number to make a point. You'll need to reference a safety standard to convert from units into millimeters or inches. 11 millimeters is not correct. 10 millimeters is not correct. 10 inches is not correct. You just need to do the analysis, work this out with an appropriate safety agency. Work this out with someone like Intertek, UL, CSA. The number listed in the appropriate standard they may or may not lead you towards is the minimum, and more is better. I specifically selected relays rated with 10 millimeters of creepage within the part, clearance as well. So even if the standard would dictate that if I need less creepage than 10 millimeters, why would I make the design worse than the components in the design? I wouldn't. That's why I didn't. This topic is difficult to navigate for me. I really want to give you the information required to make good decisions and keep you safe, but I also need to be careful about putting information out there that could be taken out of context and lead to even more problems than what would happen right now. We live in a world filled with copy and paste, just blind duplication, and that blind duplication is not a game you should play with safety, creepage, or clearance. You hear me? This is serious stuff. You're playing with your life and the lives of anyone who will interact with this device. Hopefully you're able to read between the lines there and pick up on some key points in what I'm trying to say. Establish design margin for safety. Don't just do the minimum. Use appropriate standards as a reference and do more than the minimum wherever you can. Don't take a number as a rule blindly and apply it everywhere. You need to investigate these things for every application. AC is different than DC. Different materials change things. Different environments change things. The intended use of a device will change how much creepage and clearance you need to establish. The physical enclosure plays a critical role as well. There is a right answer for every product, or maybe even a couple right answers, but every product will probably be different. Yikes. How did I get back up on that soapbox? I must really be passionate about safety or something. Weird. Coming back to the point at hand, you may notice there are two critical isolation regions on this PCB, a functional isolation barrier between line and neutral with a safety isolation barrier between main stuff and me. You may notice there is no fuse on this PCB, and that's because the fuse holder is integrated into our power entry module, but if this were directly connected to mains, like there wasn't a fuse in that, a board mount fuse would be an excellent idea. Where, of course, by excellent idea, what I really mean to say is required by every safety standard under the sun. You need a fuse. Moving away from isolation to one of our other topics, you may notice that there was no board mount power supply on the board you just saw. There's none in the layout. Yep. So what's up with that? Isolation is a big reason. Basically, the power supplies that would provide enough power with sufficient design margin were all big, they were all expensive, and they blew up my clean isolation barrier. To establish isolation with a board mount power supply, the size of this board would have probably needed to grow by about a factor of 1.5. Then you'd end up with an S-shaped isolation barrier instead of a straight one. When you're trying to achieve 10, 11 millimeters, that's basically not great. I was looking at a couple PCBA mount power supplies from the usual suspects. Meanwhile, Murata, a couple others, they're all around $10 or so. And I took a quick peek on Amazon and I saw my path forward was pretty clear here. A 5-pack of 12-volt power bricks for 12 volts that were UL listed. A 5-pack of 12-volt power bricks were $12, and those were even UL listed. Those were certified power supplies. That's a cheaper solution where both the circuitry and the final implementation already passed regulatory scrutiny, and that makes our layout a lot easier to do as well. So cheaper, better, better. Let's do that. This feels like a great solution. Now we've walked through how we hope to establish creepage and clearance for the design in our application through referencing a safety standard and implementing an adequate quantity of physical separation. At least that's what we hope. We'll need to verify the adequacy of separation through high pot and leakage current testing once a physical prototype's in our hands, but I'm feeling good in theory land, so let's continue through our journey. Let's finish this PCB. Now what? Oh, it's just some easy stuff. We worked through the hard part. Crimp terminals, some wiring, and the rest of layout. Oh right, then of course laying out the PCB for the straightforward low voltage DC stuff, which is everything except the relays and a couple terminals. Wow, let's do it. We'll put the power entry modules on the relay side of this enclosure with short cables that bring the power down to their respective spade terminal on the PCB. That seems easy enough. Keeps the mains in one spot, doesn't route it all over the place. Seems pretty clean. To complete the layout then, started with a 2-layer board as we mentioned before, and we started arranging components by group, strategically doing this to minimize the amount of crossing traces overall. And this worked out pretty great. There's a nearly solid ground plane established on the bottom layer of the board and a pretty clean upper layer too. A couple little jumpers around there, but it's not too bad. With the placement and routing complete, all we had to do was export some Gerbers, pick and place data, and upload our design to JLC PCB. Wait, what? Pick and place data to JLC PCB? Yeah, I'm just as excited as you are. We're actually giving their SMT assembly service a first look, so don't miss our future videos. We're going to get a few of these boards in the shop, and we're going to put their work under the microscope. It's going to be absolutely fantastic. We've had some mixed experiences in the past, so I'm really excited to see how JLC PCB stacks up. Unfortunately, that is all the time that we have for today. But if you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we'll be designing the enclosure for Seth and testing this design in the shop. I cannot wait! If you want to support the channel, consider checking out the products that we featured today through our Amazon affiliate links in the description. It really helps us out a lot. Thank you. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for everyone, and thank you for staying till the end. Bye!